So looking at your formula sheet, having those handy, all I want to do is to help you figure out ways to keep stuff straight. And then in the final 10 minutes, we're going to talk a bit more about that cathode ray tube, the theory of how a television works. So I wrote down here, Lesson 9 review. To solve problems correctly, ensure that you, well, first thing you're going to need to do is make sure that you convert charges into coulombs. The most common prefix we're going to use is that little mu, which is micro. What's 1 microcoulomb? That one, it's worth memorizing. In fact, that's, if kids are having to look that one up, then I know they haven't done the homework at all. You need to know what the charge on an electron and the charge on a proton is. The elementary charge, electron negative, proton positive. What is the elementary charge? 1.6. You will also need to know the masses of protons and electrons. I won't give you those. Those are on your sheet. One of the things that'll drive me crazy, Rob, is when I see a kid freeze up, say, on a conservation of energy question because they write down a half mv squared, and I see them circle the m and put a little question. I don't know the mass. It's a proton, or it's an electron. It's on your sheet. If not, I'll give you the mass. But otherwise, for those two fundamental particles, on your sheet. And then I wrote down here, make sure you solve for the correct quantity. Fill in the variables and the units in column 1 below. So let's look at this. What variable do we use on our formula sheet?
Sorry to interrupt, but just wondering, that bonus game, can you do that anytime?
As long as I get it during spring break, before the test, sure. Hey, what variable do we use for force? That hasn't changed since Physics 11. Capital F. And the units for force? Newtons. What variable do we use for field, for electric field specifically? Capital E. Can't use F, force taken. And I always choose to put a vector bar above it just to emphasize to me that it is a vector. What are the units for electric field? There's actually 2. So I'm going to draw a little line down the middle like that. Okay, we defined it as how many newtons per coulomb. And then lo and behold, when we looked at parallel plates, it turned out you could also measure it in what? From the other equation. It's volts per meter. And for both of these, don't include positive, negative signs. If you're looking for a dumb way to remember that only works this year, the first row, forces, fields, forget the signs. That first row part only works for this formula sheet this year. May not work next year in your physics, whatever classes. But for now, no signs in that first row. PE. Now, I prefer to use PE, but what does your formula sheet use for potential energy? Okay? Which is technically more correct. By the way, me using PE is wrong because how many letters are in PE? That should be 2 different variables in math. That's really unexcusable and unacceptable. Terrible math, terrible physics, but I just loathe kids getting them mixed up, so I've chosen to compromise my math standards here. I use PE and KE. That's the only time I think all year in physics that I do it. What do we measure potential energy in? Joules. What variable do we use for voltage? Well, just a capital V, but I always put the wings on it to distinguish between upper and lower case. Right? I'm trying to do a font. A sans serif, or whatever they call it, a serif. What do I measure voltage in? Well, I measure volts. Voltage is measured in volts, but how is a volt defined? Yeah. That one's sometimes handy because it helps you break a voltage apart into something else. And then we have work, which hasn't changed. It's still a W, and it's measured in joules. Now, for these two, we include positive and negative signs, the polarity of the charges. And then the last thing, there's another word for voltage. It's also called potential, not to be confused with potential energy. Okay. Let's fill in the second column, how to find the direction or the sign. For forces, how do we figure out what direction we're talking about? Because forces is a vector. We decide either before or after the fact. It doesn't matter. I usually try and roughly figure it out before. How do we figure out which way the forces are acting? Two key words, like and unlike. Come on, help me out. Like. Okay, ready? Two key words, like and unlike. Like, repel. Unlike,
This Friday, I can be at GH.
I don't know, I'm teaching right now. Little attention span, boy. Patience. How do we figure out the direction for electric field? This one was a bit more complicated. This one we actually had to define because there was no official direction that automatically popped out. We said, okay, so that we all have the same direction, here's how we defined it. How did we define it? Which way would my abbreviation for positive is a plus sign with a VE next to it. My abbreviation for negative is a minus sign with a VE next to it. If I just see a plus sign by itself, I assume it's an equation, but if I see a plus sign with a VE, I assume it's a noun or a verb. Adjective. Positive, adjective, I guess. Which way would a positive charge want to move? Which really means from positive to negative. Sam, I don't use that one because often you won't have both a positive and a negative in your picture. You only have one or the other. Well, then you imagine a little tiny positive test charge at that location. You can figure out like or unlike, repel or attract, which way would it want to go. So I'm also trying to tie it into the previous one. How do you find the direction for potential energy? It's a trick question. It's a scalar. Oh, here it's going to be and include signs, include signs. I guess I didn't need to make that big note over on the left. I forgot that this was coming, but still it's worth repeating. All right, let's try doing the equations here. So let's do, you know what? Let's fill in this whole next row, the forces row. What's the equation for the force between point charges? This was what we called Coulomb's law. We said that F equals K Q1 Q2 over R squared. We noticed it looked an awful lot like gravity. That got our minds to thinking for a little bit, dreaming. What's the equation for force between parallel plates? There is one. It's on your formula sheet, but you have to rearrange a definition. This is the equation for force that works for anything. So find the other equation that has an F in it and get the F by itself. Equals what? I don't know what you were looking at. The charge at that location times the electric field at that location. By the way, that's really the equation for force, not this KQ1, Q2 over R squared. Well, wait a minute. Watch, I'll show you that actually it turns out this equation contains that one. We'll show that in just a second. What if you have multiple charges? So what if you wanted to find the net force on this charge here? Don't write this down. I'm really going to scribble on this diagram. You would temporarily ignore that charge. In your mind, scribble it out. You would find the force, magnitude, and direction from this guy on that charge. Maybe it's to the right. Maybe it's to the left. But it's got to be one or the other because like repel, unlike attract. You would then, in your mind, cover up that guy. You would find the force, magnitude, and direction from this guy on that charge. Like repel, unlike attract. Up or down. Then you would add those two forces together vectorially. I don't know if that's what the picture would look like, but you'd add them vectorially. So what I'm going to write down here is add vectorially. I'm not sure if that's how you spell vectorially. I'm not even sure if that's a word. Take the word Victoria, replace the initial I with an E, and then make it an adverb. Now, it doesn't necessarily have to be tip to tail. It will only be that if they're not on the same level. I think I gave you questions in your homework, and you can expect it on your test, where they're in a nice straight line, in which case I would let one direction be positive, one direction be negative, and I would go winner minus loser, or winner plus winner if they're all in the same direction, or loser minus, well, make your biggest force your winner. It's easier. The second thing we have here is electric field. Electric field. So electric field from a point charge was what? KQ over R squared. That is if you know the planetary charge that's giving off the electric field, that's creating the electric field. And Dylan, this is why I said that this equation is actually the universal one, because if I plug this into the E up here, then I'll get K, big Q, little q over R squared. I'll get that equation. It's contained and hidden inside there. What was the electric field between parallel plates? The voltage you travel through divided by the distance between the plates, or the distance that you've traveled. Is that okay? Oh, there is actually a third definition for electric field. This first one is if you know the planet that's causing the electric field. This second one is if you have a point in orbit somewhere and it's inside an electric field, you don't know what's causing it, but you can measure the force that that point is feeling. The force divided by the charge at that location will tell you the electric field at that location. And once again, we use the principle of superposition. You would do one charge at a time, one point at a time, and you would add them vectorially, magnitude and direction. If they're in a straight line, and I will on your test give you at least two charges in a nice straight line and say to you, find the electric field somewhere. If they are in a nice straight line, winner minus loser. Or if they're all winners, just add them up. How do you figure out the direction? Which way would a positive want to move at that location if it could? one charge at a time. Potential energy. That's K Q1 Q2 over R. Don't forget to include positive and negative signs. Where did we have zero energy? Out at infinity. What was potential energy between parallel plates? This is the one that we started using last day. And if you're not sure, you can figure it out by looking at your definition of voltage and getting the energy by itself. Dylan? That's also technically Q change in voltage, but almost always we were going through the whole voltage anyways, so we just looked at the overall voltage. So what if I gave you those three charges and I said find the energy of that system? I would find the energy between those two, including positive and negatives. Magnitude only because it's a scalar. I would find the energy between those two, including any positive and negatives, magnitude only because it's a scalar. I would find the energy between those two. Now I would need the distance between them. I might have to use Pythagoras to find it. And then just add them up. No vectors. Woohoo! Voltage. Well, we had two ways to find voltage. First of all, from a point charge. That was the voltage, KQ over R. Include the sign. How do we find the voltage between parallel plates? This one is so obvious that it's tricky. They usually gave it to us in the diagram or in the question. So I'm going to write down here. Usually given. That's a fib. The next unit we're looking at is circuits. And in the circuitry unit, I would have no problem giving you some kind of complicated circuit, not telling you the voltage, and you'd have to, using your circuit rules, using Ohm's law and Joule's law and Kirchhoff's laws, next unit, you'll be able to figure out what voltage it must be. But for now, Shashan, it's almost always going to be given. I guess the only other way, though, occasionally, you could say, well, voltage is the amount of energy per Coulomb. If I gave you a situation where you were using kinetic energy, is there a change in height? Is there a change in speed? And I gave you the initial and final speeds, I could say, how many volts do you need to get it done? And you would solve for the voltage. Fair enough. Voltage is a scalar, so again, add them up. You'd find the voltage from that guy at that point. You'd find the voltage from that guy at that point. No tip to tail required. Add them up. And then we have work. We can't really use force times distance. We certainly can't with point charges. Can't use work equals force times distance with point charges, because as you move further and further away, or as you get closer and closer and closer, what happens to the force? It changes. Okay? So we have to, for point charges, use change in potential plus change in kinetic. Now, for plates, technically, you could use work equals force times distance, where F equals ma. The only problem with that is now you need to find A. Well, what's VI? What's VF? You can. I still tend to use the same thing. Work equals change in potential plus change in kinetic. Reason being, Cole, is change in potential is QV. That's pretty easy to find, as opposed to F equals ma. I know the mass. It's a proton or whatever. What's A? VI is 0, VF is, I don't know. Oh, I better go with conservation of energy to go find VF. Okay, half mv squared, blah, 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 the square root. Okay, now I got VF. What's the distance? You know what? It's easier just to jump down to this one. So I wrote down here, fill in the final what we already have. Reason why we can't use force times distance for point charges. And then I wrote down here, what's the reason that we can use parallel plate work using force times distance or change in energy? Force is constant, but I gotta be honest, I just prefer to use the QV. It's cleaner. I wrote down here the very last thing, add your vectors to find your total force or field, or add your scalars to find your total potential energy or voltage. Fill in column 5. We already have. Let's do an example. For the charge system below, find the A, force, magnitude, and direction of the positive charge. B, voltage at that location. C, work required. We're going to add one more. We're going to add a electric field. So I think I can do A right here. F equals K Q1 Q2 over R squared. F equals 9 times 10 to the 9th. Oh, by the way, again, that's microcoulombs. That's supposed to be microcoulombs. Yeah, I'll have to redo these diagrams. They're on their last legs. What's charge 1? This one here? Sorry? I didn't hear you.
1.5.
Yeah, no negative because we're doing a vector. Charge 2, positive 4.2. Careful, what's your distance? What's your radius between these two? 36 is wrong. So if it's centimeters, what am I going to put? 0.36 squared. How many newtons of force is there? Oh, and they specifically said find the force on the positive charge, so that's how I'll define my direction. Do you get 0.4375? Or 0.438 newtons? Direction. So we want the force on that positive charge there. Which way does that positive charge want to move? B says, find the voltage at the dot. How many charges are there in this question? How many voltages are there in this question? 2. I'm going to find the voltage from charge 1. I'm going to find the voltage from charge 2. Both of these are going to be K Q1 over R1, K Q2 over R2. They're going to be KQ over R. 9 times 10 to the 9th. Charge 1, negative 1.5 microcoulombs. All over 0.12. and I get negative 112,500. Volts. Voltage 2. 9 times 10 to the 9th. Positive 4.2 times 10 to the negative 6th. All divided by 0.24. I get 157,500. Yep. What's the total voltage? 157,500 plus negative 112,500. I get a total voltage of 45,000 volts right there. Is that okay? Yeah. Ah! Nothing there. I got show. C. Cammy, what's C asking me to find? Change in potential plus change in... Well, hang on here. So I started out going work equals change in potential plus change in kinetic. And I think what we're talking about is starting at rest and ending at rest. And I think it's when it says find the work required to put a 4.75 times 10 to negative 8 Coulomb charge at that dot, I think we're moving it from a very, very far distance away. Yes? You get a little delivery service now? Boy, I should have asked for one. We're starting from a very, very far distance away, coming in close. How much energy do we have to start out at? If we're starting in a very, very far distance away, 0. I started out going this, and then I was going to go change in potential, final minus initial. Wait. What did we just figure out in part B? The voltage at that location. I think as a shortcut, we can say, aha. Because what do you think the voltage is out at infinity? If voltage is how much energy you have per Coulomb, and you've just told me that out at infinity I have no energy, what's my voltage out there? 0. What's my voltage at this dot? No, what's my voltage at this dot? What did we find in part B?
45,000.
So if I start at 0 and end at 45,000, how many volts have I moved through?
45,000.
Okay, why don't I use this then? Way less than, I mean, I could go through this whole K, Q1, Q2 over R potential energy rigmarole again, but nice, let's use this. How big is the charge that we're moving? 4.75 times 10 to the 8th. Negative 8, sorry. That'd be a huge charge if it was times 10 to the 8th. Times 45,000 volts. How many joules of work will this take? Times 4.75 times 10 to the negative 8. And I get 2.14 times 10 to the 2.14 times 10 to the negative 3 joules. D, electric field at this location. How do I find electric field? Well, that's going to be the electric field from charge 1, and it's going to be the electric field from charge 2, both of which are going to be KQ over R squared. KQ over R squared. But it's going to be Q1 R1, Q2 R2. By the way, do you notice this looks almost identical to the voltage equations right above it? Except instead of an R on the bottom, what do you have? Zach? R squared. Don't get them mixed up. Every year some kid does. I don't know how to prevent it. So all I can do is yell in advance, don't do this. So it's going to be 9 times 10 to the 9th. Do I put in negative 1.5? No. Nine times 10 to the 9th times 1.5 times 10 to the negative 6 divided by 0.12 squared. And I get an electric field of 937,500. Newtons per Coulomb. Direction. So right now, I'm ignoring this charge. At that dot, which way would a positive want to move if it could? To the left. Let's do the same thing for charge 2. 9 times 10 to the 9th. Ignore the sign. 4.2 times 10 to the negative 6. Divided by 0.24 squared. Change that to a 2.4. Change that to a 4.2. I get 656,250. Let's try that again, Mr. Dueck. Newtons per Coulomb. Direction. Cover this guy up. Which way would a positive charge want to move if it could? Left. Did you say gauche? These are in the same direction. I'll just add them up, winner plus winner. What if they were in opposite directions? Winner minus loser. Yeah. But this, that, plus 937,500. I get 1.6 times 10 to the 6th newtons per Coulomb. Is that right, Mr. Dueck? 1, 2, 3, 4, 5. Yep. 1.59 times 10 to the 6th.
There'll be a question like that on the written part.
Absolutely. Guarantee it. I like this question. I like this question. I like this question. I like this question. Hello, question. How are you doing? You want to go out for dinner? I really like this question. We're going out on at least a date. Turn the page. Let's look at the TV again. Can you wait for 10? Okay, it's nearly done. Example 8. Remember the cathode ray tube, the TV? We looked at this on Friday. Let's look at it in a bit more detail. So, below is a side view of a cathode ray tube, a CRT, and the front view of the screen. Now, for the purposes of this question, Jimmy, we are going to assume that you are sitting in a chair watching, facing that way. Okay, just our reference point, because sometimes kids are we looking from the back of the screen or the front of the screen? We're going to assume you're sitting in your room looking straight ahead at your TV. Here's our setup. Here is our accelerating plates. Remember, we said this. You can make this negative, charge this positive. Emily, this is also a big negative plate right there. Don't write that in. We also put a big negative plate right there. Don't write that in. That way we can push it towards the middle very, very easily. We can get a nice electron beam. But now we're going to go three-dimensional. So we have our upper and lower plates. These can deflect the electron beam up and down, but we also have a set of plates that set up vertically so that they can deflect the beam to the left or to the right. We can now position a beam very accurately. Okay? When we turn the gun on, but we don't turn the plates on, we get this situation right here. We get it hitting dead center. Now let's see if we can reason our way to some answers. It says this: where will the electron dot end up? Choose from location A, B, C, D, or E on the diagram if we, number one, make the upper deflecting plate positive. If I make this plate positive, how will that deflect the electron beam? Right now it's in the center. I make this positive. Where will we see it hitting? Location A, B, C, D, or E? I heard it here. Why A? So if we make this positive, which way will electrons want to go? Up. They're going to get bent towards it. They're going to leave it at an angle kind of like that. They're going to hit right about there. I think if we make the upper plate positive, we'll get a bunch of dots at location A. Okay, reset it back to 0, 0, so we're hitting dead center again. Now we're going to make the right plate positive, this one here. How do you think that would deflect the beam? Which one, D or B? B as in boy or D as in dog? Boy. Boy, you're right. Absolutely. This would pull the electrons to the right, so you would see this dot move from dead center over to the right. Absolutely. What if I make both the right plate and the upper plate positive at the same time? E. Okay. Let's reset this. Now we're going to adjust the voltage so that when the plates are turned off, we give the upper plate a tiny positive voltage so that we're hitting a little bit above center to start out. Where will the electron dot end up? Choose from A, B, C, D, E, F, G, or H. Sorry, A, B, C, D, E, F, or G. Get that later. Follow this stuff for now. Where will this end up if we... Okay, what if we increase the deflecting voltage? So right now we have a deflecting voltage that's hitting right there. What if we bump that voltage up? So what of those would be more? G. What if, second option, I reverse the polarity of the deflecting voltage? So let's go back to here where we started out, but I flip it so that the bottom plate is positive and the top plate is negative. See? Ooh, third one. What if I go back to here, so we're hitting right there. What if instead I increase the accelerating voltage so these electrons are leaving faster? What do you think that would do? Deflect it more, less, or the same? Less. Why? How come? They're going faster, so what variable does that affect? I think that affects the amount of time between the plates, which means that the amount of time that force is acting on them for is shorter. There's less time for them to accelerate up or down. Okay? Does that make sense? I think it would be A. In your study guide, in your big ultimate review package, I think there are a couple of questions about the cathode ray tube. I won't be asking you cathode ray questions on your test yet. This is how cathode ray tubes started out, being deflected with parallel plates. And then eventually engineers said, hey, wait a minute, there's a better way to do this. The problem with the parallel plates is they take up length. It meant your TV had to be big. Then they realized you could do the same effect, but instead of deflecting it with parallel plates that were charged, you could deflect electrons with magnets. And magnets you can build really, really small. It lets us make the material shorter. So in a couple of units, when we start looking at magnetism, we're going to come back to this cathode ray tube and actually do it properly with solenoids. And that I will be testing you on. So I always start out showing you the original way. But the technology for a black and white TV, well, It says explain your answer using principles of physics. I think we just did. Turn the page. So how does our simple model of a CRT explain how black and white television works? Only one dot or pixel is hit at a time. By sweeping the Y voltage from positive to negative, we can move a beam up and down on this phosphorescent screen. By sweeping, we can step the beam over using a tiny X voltage and then sweep the beam up and down again. Then bump the beam sideways a tiny bit, sweep it up and down again. Bump the beam sideways a tiny bit, sweep it up and down again. If we do that really, really fast, your eyes won't notice it. If we gradually add increments of X voltage and then sweep vertically, we illuminate the entire screen. The TV signal turns the cathode ray tube beam on and off as it sweeps the screen. Beam on is a white dot. Beam off is a black dot. Beam weaker, partially on, is a gray dot. And your eyes, Shashan, put that together and see a picture. And then we saw a video last day for a color TV. We said there's 3 different electron beam guns. You get your RGB, your red, green, blue approach. What's your homework? Here is what I assigned with my block A's. 2, 4, 7, 9, and 10, and 12. 2, 4, 7, 9, 10, 12. Let me write that down. Number 2. Number 4. Number 7. Number 9. Number 12. Otherwise, last thing.